Chapter 11 is all about the difference of population parameters, and we're going to look at three different situations with differences. First, we're going to look at difference of proportions, then we'll look at difference of means, and there's two different cases in difference of means, either unpaired means or paired means. Now, when we're looking at the difference of parameters, the logic is a little bit tricky to follow. So I put a page here just to explain some of the logical connections between the hypothesis test and the interval, the confidence interval for the difference of the proportions on this one here. So here, this statement here is an important one. If a confidence interval for the difference of proportions P1 minus P2 contains only positive values, then P1 minus P2 is greater than 0, and you add the P2 to both sides, and you can all say that there's a relative size difference between those two proportions, so P1 is greater than P2. It's sometimes hard to notice that it only contains positive values, so sometimes it'll be like, they'll write it like this, 3, 5, so like 3 to 5, all the values between those two are positive values, and in that case you have that relationship between those two parameters. In the opposite way, if P1 minus P2 is less than 0, then you add P2 to the other side, we get P1 is less than P2. So the opposite way. And we could see like 0 here. We have negative, let's just say 2, and lower limit negative 5. So like that may be written negative 5, negative 2. Like that. So if it contains only negative values, then we can say the relative sizes P1 minus P2, you have P1 is less than P2. Now, if the interval contains both positive and negative values, then we can't really say any definitive conclusion about the relative sizes of those two parameters because it contains 0. So like if it goes from, let's just say like negative 2 to 3, it contains 0. So if 0 is a possibility, P1 could equal P2. Now, it's a lot more straightforward with the hypothesis test because it's directly embedded in the alternate hypothesis, those relative sizes. And very often what I like to do is just run a hypothesis test before I do a confidence interval. And you can kind of see the connection between those two. So like in a situation, just for example, in a situation like this one here, this first one here, where the confidence interval contains all positive numbers, we would end up in the hypothesis test rejecting the null hypothesis. Same thing for this one, we would reject the null hypothesis in favor of the alternate hypothesis, which would be this one here. If the confidence interval contains 0, we would fail to reject the null hypothesis. And of course, this is if you have the equivalent, it would have to be a two-tailed test, and it would have to have like the complement, 95% would have to be paired with a 5% level of significance. Okay, now the steps are a little bit more challenging in these just because there's multiple steps that you have to do. Especially with the normal criterion, like random sampling is the same, and independent sampling, now you just have typically two populations. Sometimes it's just from one, but typically you have two populations that you're comparing to. For the normal criterion, you're doing the same check, but twice. So like n times p times 1 minus p, but you're doing that for both p1 and p2. Okay, couple other things. We're not going to be doing this by hand, but if you would want to do it by hand, which I don't recommend, you can follow these steps here. The one thing, this is kind of a new thing here. This is usually called the cumulative proportion, and you take the successes in both populations, add them together, and divide by the total sample size. Just add both the sample sizes together. It's used in the calculation. That's pretty much the only place that it's used. It's calculated in the Excel file as well if you ever need to identify it. But it's just you add the numerators together, add the denominators together. Okay, now we're going to be using Excel, and the interpretation is fairly similar. We're going to be using this logic on the first page pretty often with confidence intervals as well, but I usually like to run a hypothesis test, which gives us that conclusion instead. We were just looking hypothesis test. Here's the confidence interval. It's really similar. The conditions, and then this computation is complicated, as you can see here. It's a slightly different formula. But yeah, we're going to just use the Excel file for this because it's very easy to make mistakes in this process where there's so many steps, and most people just program this stuff anyway. Okay, so let's look at a couple examples. It says a college wants to increase their retention rate by trying a new plan. A group of 500 students went through the new plan. 334 of them continued their studies the following year. A group of 600 students did not go through this new plan, and 382 of them continued their studies the following year. We want to perform a hypothesis test with a level of significance of 5%. Okay, so our first step is to check the conditions. And this will actually be good for both part A and part B, since they're the same conditions. First, we can assume random sampling was used. Perhaps check with whoever was running this retention program just to make sure that they actually understand what random sampling is and that they ended up using it. And now for the normal criterion, we need to look at the p-hats. So let me just note here's what they are. So note for p1 hat, which I'm just going to label as well the new plan, just put new there. We have 334 out of 500, and that gives us 0.668. And for P2 hat, which I'm just going to put like the old plan. They had retention rate 382 out of 600, which is 0.636666, and so on. At that point, we don't need too many decimal places, but it's good to keep as many as you can. Now we check n1 p hat 1 times 1 minus p1 hat, or p hat 1, however you want to say it. And this is 500 times 0.668 times 1 minus 0.668. And that gives us 110.888, which is definitely greater than 10. Just good. Now, n2 p2 hat. This is 600 times this 0.6366667, and 1 minus that. And this gives us 138.793. Which is definitely greater than or equal to 10. So both of those are greater than 10, which means our sampling distribution in this situation is approximately normal. Now, for this last one, well, I'll just assume that 500 and 600 are less than 5% of all the students at the college. We don't exactly know that, but we can assume that it's hopefully a larger college. And with all those conditions met, we're good to go. Just gonna put a little box around this. There we go. We have our conditions met. We can move on to running our hypothesis test. So I'm going to set this up. I'm going to put our null hypothesis first. For the difference of proportions, it's always P1 equals P2. I'm just going to label this with new and old. I think it's a little bit easier to check the direction when you do it this way. So P new, P old, we have to choose a direction. They think the retention rate will be higher. It will increase with the new plan. So we think that the new proportion will be higher than the old proportion. And I just put my greater than symbol between those two. Okay, now we're going to be using the hypothesis tests Excel file. And we're going to use the difference of proportions sheet. Okay, now I'm going to navigate to that sheet and use it to guide me. So at the bottom, difference of proportions down here, there's a bunch of things that we need to fill in. So I'm just going to write those down here. So p hat 1, which is the new one, p hat old, n, the new one, n for the old one, the level of significance, and the tail we know is right tail. Okay, so just copying those down from the Excel sheet. And now I can fill in what these values are. For the new one, it's 334 out of 500. I'll just do that in Excel. And then for the old one, it's 382 out of 600. 500 for the new, 600 for the old. The level of significance was 5%. 0.05. And I plug those values in, which will then give me my p-value. So let's plug those in. And I'm going to do the division here. Equals 334 / 500 equals 382 / 600. Put 500 in there, 600, 0.05 is good. And we're doing a right tail test. Our p-value ends up being 0.1388437. So pretty high p-value, 13%. Our conclusion in this case would be that we fail to reject the null hypothesis. Yeah, so we fail to reject the null hypothesis. Because we failed to reject, I can write a conclusion. Just going to draw a line over here. And I'll say we don't have significant evidence that the new plan increased the retention rate. The evidence isn't quite strong enough. Okay, now for this next part, create a 95% confidence interval for the difference of proportions. This is really similar. So I'm just going to right here, we're going to use the confidence intervals Excel file. And we're using the difference of proportions sheet. And it's set up in a similar way, so you're actually plugging in these same 4 things. So those 4 things, and then the only other thing we need to plug in is the confidence level. But let me show you that. Make sure you go to difference or proportions at the bottom. I'm gonna take those first 4 things, copy them, and paste them over here. You can see that they're the same things. They have the same names in this file. And then the confidence level is 95% already. So let me just note that. .95 I put in there. So that gives me then the lower limit and the upper limit. And it's negative 0.0251 and positive 0.0878. Okay, so that's the confidence interval. It does contain 0. There's positive and negative values for our lower and our upper limit. And because of that, it's kind of the same conclusion that the relative sizes, we can't really tell which one is bigger. We can just write this. We are 95% confident that the difference of proportions between the new plan and the old plan is between, I'm going to rate them as percentages, negative 2.51% and 8.78%. And this contains 0, so we can't really say much about whether it increased or decreased the retention rate. Okay, so here's another one. And this is actually from an AP test. So this class has a very similar curriculum to the AP statistics curriculum. Scientists use metal bands to tag penguins. Do the bands harm the birds is the question. Researchers investigated this question with a sample of 100 penguins near Antarctica. All these penguins had already been tagged with RFID chips, and the researchers randomly assigned 50 of them to receive a metal band on their flippers in addition to the RFID chip. The other 50 penguins did not receive this metal band. Researchers then kept track of which penguins survived for the 4.5-year study and which did not. They found 16 of the 50 penguins with the metal band survived, and 31 of the 50 penguins without the metal band survived. So the first step is, it says calculate the difference in proportions of those who survived between the two groups. So I'm just going to write here, I'm going to label these P hat metal, and that's 16 out of 50, which gives us a 32% survival rate. So not very good. I'll put no metal for this second one. And this was 31 out of 50. So 0.62. And if you subtract those two, so I'm just going to make it positive, make it a right to one. So I'll put no metal minus p hat metal. We subtract those two values, 0.62 minus 0.32. And that gives us 0.3. So the difference of proportions is 30%, which seems pretty significant to me. Okay, now it says perform a one-tailed hypothesis test for the difference of proportions and explain as if someone has not studied statistics what the p-value means. Okay, so the conditions, we'll just assume that they're met. It says random assignment, so we'll assume that the penguins were chosen at random, and then they were also assigned at random. The size of the sample should be all right. And then the last condition, there's lots of penguins, so just 100 in comparison. So we'll just assume the conditions are met. It says to perform it either way, so we'll just go through with it. So the null hypothesis is that those two proportions are equal. And we do keep the hat off of it in this because this is talking about the population parameter, not the statistic. So the p metal is greater than with the metal band. And we're using the difference of proportions. Let's make this a little smaller. And for this, we have these to fill in. And we know those are 50. We calculated them before, so 0.32, 0.62. The only other thing we need is our level of significance. So, oh, and it actually doesn't give us one for this one. So we actually have a choice of what we can use for this. I'm just going to put 0.05. It's kind of a standard 5%. And I'm going to go here. Make sure you switch the sheets. We got to go to hypothesis tests. And we're changing these 0.62, 0.32, 50, 50, 0.05. And this one is a right tail test. And we get our p-value down here, just pretty small, 0.0013261. I'm just going to copy that down. here. Okay, now our p-value is small, and it says, explain as if someone has not studied statistics. Well, we're gonna try our best with that. So I'll just put here, this is the probability that the difference of proportions is as extreme as or more extreme than what the data show. And I guess I'll write another sentence here. So it's the probability that the difference we saw is just due to chance. Since this is so small, it's likely that the middle bands had an effect on the survival rate. Okay, maybe not the best explanation. But this, I kind of like this one a little bit better. The probability of chance, like that name of the p-value is a good way usually to explain. Maybe more emphasis on like the survival rate would be warranted, but that's all right. Okay, now summarize your conclusion from this p-value. Do the bands hurt the penguins? Be sure to address the issue of causation as well as the issue of significance. Also justify your conclusion. Okay, so we would, in this situation, since the p-value is less than the level of significance, and we'll just assume 5%, we reject the null hypothesis. And I'm just going to do like the standard conclusion that we usually go with. So we'd say we have significant evidence that the proportion of surviving penguins with metal bands is less than the proportion of surviving penguins without metal bands. And we can say we think the bands do hurt the penguins. Or lessen their chance of survival. So I just want to make this a little bit smaller. And write another statement here. So we can pretty confidently claim causation since the penguins are all in the same location. And were randomly assigned. Either to have the band or to not have the band. The only difference was the metal band in those two groups. Another supporting factor of this is the p-value was very small. Which shows strong evidence against the null hypothesis.